Good afternoon and welcome to today's webinar event. Today we're going to be discussing silicon elastomers with Alchem, who are specialists in this very topic. Silicons are a pretty novel material when it comes to 3D printing, one of the lesser used materials. Well, we're going to talk a bit today about the chemistry of those materials, the applications, and of course the business cases for working with this particular class of material. Now, joining me today are two experts in this very topic. We have Dr. Damien Gigian, who is the lab manager of the Additive Manufacturing Lab in Lyon of Alchem Silicons, and also Carsten Schlichter, who is the program manager of the AM project at Alchem Silicons. Now, Dr. Damien Gigian studied chemistry at the French Engineering School of Clermont-Ferrand and specialized in rubbers and thermoplastic synthesis and aging mechanisms, whereas Carsten Schlichter has been working in the silicon industry for over 30 years and has held a wide range of positions. For those new to the platform, and this is the first time you're using Remo, I'd just like to give you a brief tour. You will see on the right-hand side of the screen, there is a chat window where you may say hello to everybody, tell us where you're from, communicate with your fellow attendees. We'll be using that function throughout the event, and also in the same window, but if you click on the Q&A function, you'll have the option to ask questions of our guests. And I would encourage you to make use of that Q&A function. Type your questions there. You can vote up the questions you'd like answered as well. And we will be pausing several times during today's presentation to take those questions from everybody who has something to ask. Also, the presentation will be followed by a networking session. Please do stay for that. We have representatives of Alchem on hand who will be able to answer any specialist questions you have, talk more about the use of silicons in additive, and I'm sure they'll be very keen to answer anything you may have to ask. Okay, so right, let's pull up the agenda for today then. Okay, let's get that agenda up on the screen. So, Damien, if you could launch the agenda, please. Here we go.
So.
It's good to see so many people joining us from across the world. We've got people from South Korea, Germany, Paris, Greece. This is it's great to see the additive manufacturing community coming out for what's actually a lovely sunny day in London here. So here we go. Right. So let's have a quick look at the agenda for today. Marvelous. So right, as I've said, Carsten and Damien will be presenting. And I think on that note, let's hand over to Carsten, who can actually start taking us through the program. Over to you.
Yeah, thank you. Thank you for the kind introduction, Michael. Hello, everybody. So my name is Carsten Schlichter. Thanks for joining this webinar. I'm together with my colleague, Damien Gigian, and we are going to walk you through this agenda of today, additive manufacturing. So walk you through Alchem in the silicons industry, silicons in additive manufacturing use cases, and then going back to hopefully a lot of questions when we are going to conclude. So for some of you, this might give insights into a new way of using silicons. To others, it might become a discovery of silicons as a high performance material. And to even others, it might give a point of to both aspects in that respect. So starting from there, if you take a minute just for those who are knowing already about silicons. If you can raise a hand in the chat, that would be nice, just to have an idea how many silicon specialists we already have around the table, and going from there. So let's start with having some words about Alchem. So Alchem is a Norwegian company with a headquarters in Oslo, but we have major hubs in France and in China. We are a global company operating out of 29 production sites, as well as R&D centers and offices worldwide, from Brazil to North America, from Europe to Asia Pacific, always being close to our customers in order to provide them the best solutions based on silicon chemistry. We have a global team of roughly 6,800 people with a turnover of $2.9 billion, which is a fairly reasonable size. And out of that, very important for us, we have over 500 people working in R&D that are here to shaping a better and more sustainable future by providing innovations, especially when we go into specialty applications in that respect. So Alchem has 3 divisions. Next, please. We have 3 divisions: silicon products, and carbon solutions. Carbon solutions is the smallest division, taking 7% in turnover of Alchem into that. They are specialists in producing electrode paste based on an innovation that is over 100 years old, but still valid for many industries that have furnaces and smelters out there. The second biggest division is silicon products, with roughly a turnover of $1.4 billion. This division is, besides supplying silicon metal to ourselves, the silicons division, they also have advanced materials for many industry, from oil and gas to automotive. You will find them in solar panels, but you will also find their advanced material in the rover that is exploring Mars at the moment. And as well, you find them in application in constructions. For instance, we'll find them in the Burj Khalifa in Dubai, so in the highest building that we have at the moment on the planet. So the third, finally, the division is where we are belonging to, is the silicon division. So we have a turnover of $1.5 billion, and we are one of the leading fully integrated manufacturer of silicons that we provide today with into many markets. So I would say, as global as the presence of Alchem around the globe, we have as manifold is the ways of using silicons in those very diverse markets. Next, please. So the thing out there is that based on those diversities, we see the unique characteristics and properties of silicons that can use out in various and many industries, directly or indirectly, from chemicals to electronics, from healthcare to energy, transportation, consumer goods. Silicons are accompanying you all day long, knowingly or unknowingly. Take an example. You take a shower in the morning in your bathroom, and you will have there joints and seals and profiles made out of silicon for water tightness. You take your shampoo, your makeup, and you have silicon containing formulation. You take your car driving to the office, and you have an airbag that has a silicon coated fabric into that. And when you arrive at the office, maybe you take an elevator to your office floor, and you see the emergency signs. And those emergency signs, they are linked via safety cables made out of silicons in order to have things right when an incident might occur. So we have it all day long, even to the pizza at night, taking a food grade paper that you would use then in front of watching the late night show by your latest generation TV at your broadband cable that has silicon treatment in order to for that. So this is the world of silicons in a snapshot. And if we take that further now into more about silicons in additive manufacturing, we can frame it a bit more about in general terms before going into more details. Next, please. So when we're talking about additive manufacturing silicons, we start in general all about global megatrends that are leading us, and we have all been talking about these megatrends for many years. So sustainability now is clearly a key point for decision making, and it's not just for strategic point. I think we all agree that today it's really related to the investments that we are taking, investment decisions that we are taking on a regular basis in this area. If we take an increased standard of living, aging and growing population, this is where we are looking forward to have new materials that allow the development of better solutions that are needed for tackling the requirements of the future in many areas where we need better solutions to be provided. And digitalization and additive manufacturing is really the direct link, where we see that this world in additive manufacturing is based on the digital world, where we see data communicated from maybe a DICOM to a printer machine, or from the CAD to a printer machine, where we have this part that we will see coming out now with this material of silicons also as a novel material being able to be used in the factory of the future. So what we have seen over the years in materials being available that are primarily rigid materials like metals, like plastics, now we're talking about soft materials, elastomeric materials, and specifically silicons with their unique characteristics and properties. So we name it in waste reduction, new business model, technology, innovations. That's really the world where we would like to use silicon as elastomers in a very efficient way, but the possibility to use silicons in a direct print, not what we know until now in molding, injection, which for sure will pertain, but will open up a new way of silicons, also a new way of really providing a business model where we don't have to build up on economies of scale, but we can build up on small runs, personalized items that are becoming more and more asked for. If you go forward in technology innovation, as said before, we need those. We are going forward to those because additive manufacturing will allow, together with silicons in the elastomeric world, the progress into new parts that haven't been able to be designed by the traditional modes, but that will be needed to pursue future innovations. And a major point for us in silicons, as silicons are a biocompatible material and very interesting in healthcare, it's down to personalized healthcare, where we see a lot of possibilities of using that, because we are all equal in a certain sense, but we are not equal if we talk about biology as a general item into that. So based on this frame in general, that's what we have been looking for when we were talking about having a project of silicons for 3D printing at Alchem. And that's what we want to show you now in a more technical point of view, in order to make you more familiar with what we are going to propose to do and what we are talking about today in this webinar on the technical side. Handing over to Michael.
Right, Carsten, thanks for that great introduction to the very large topic there. We've got a few questions coming in already, so let's see if you can help me with these ones, please. So where are silicons mostly used in additive at the moment?
In additive at the moment, I would say, yeah, prime use might be in healthcare, but industrial applications are not far behind. So there's not a real forerunner if we take those both applications.
Do you require a specialist 3D printer to work with silicons?
Yes.
Okay, short answer. I'm sure we're going to come to that a bit more in the technical session as well. So we'll answer that a bit more in depth. And the final question we have from the audience at the moment is, are 3D printable silicons already commercialized for industrial usage, or are they more at a proof of concept stage?
Yes. Short answer. Short answer. Yes. Yes. We have a range, and I think that's for Damien. He will touch on this point during his presentation, and it's not just proof of concept. We are beyond that.
Great. Okay, on that note, let's get Damien onto the stage then, and can tell us a bit more about the technical side, please. So Damien, if you'd like to turn your camera on.
Let me check. I have to do something to...
Here we go.
Hello, everyone.
Hello, we can see you. And then let's get the presentation back up. Just a reminder, you please do send your questions in throughout this. We'll be taking another break for questions after Damien's section on the technical nature. I think you're ready to go now.
Okay, it's okay?
It's good. I can see it, yes.
So after the introduction done by Carsten, we will go now through the technical part. And especially the main question here is how silicone elastomer can bring more value to additive manufacturing. So today, probably you already know that you can print, I would say, soft parts with additive manufacturing. To do that, you will mainly use thermoplastic elastomers. It's more or less like a rubber, and with relatively high hardness, and at least up to, from 70 Shore A. And this kind of technology show no really durable performances, especially faced to high temperature. So in consequences, this technology is mainly used today to print prototype, soft part prototype. In front of that, you have the silicone elastomer technology. This technology presents outstanding performances with very good durability faced to different aging conditions, and present also biocompatibility. And thanks to these properties, I will show you how silicone elastomer can help you to print functional parts today. So what are the key characteristics of the silicone? The silicone products are based on two chemistries. The first one, mineral chemistry with silicone material, and the second one is the organic chemistry. And if you combine together these two chemistries, you will get the basic structure that you can see on this slide on the right. And this structure present very good performances, especially on a wide range of temperature. You can use it from -80 to 250 degrees Celsius or more. This structure presents also a very low glaze transition that leads to very soft material. For sure, the durability is very good, especially faced to natural aging. like oxidation, UV exposure, or ozone. Also, you will have a very good fire resistance of silicone material and a release of non-toxic smokes if you burn it. The other properties are low surface energy, but also exceptional harmless. That's why we use from many years silicone elastomer for example, for healthcare or also food contact application. So if I come back to the comparison between thermoplastic elastomer versus silicone elastomer. So today you will find the thermoplastic elastomer to print soft part as filaments or pellets, and you will melt it or fuse it during the printing process by extrusion, for example. So this transformation is reversible, and that's why also this technology is not suitable for high temperature application. However, silicone elastomer, you will find it in liquid state or past. It's a non-meltable. You will extrude it directly like that. But during the printing or after the printing, you will cure the material in order to get from the liquid state to the elastomer. So you will do a covalent cross-linking during this process. This is an irreversible transformation. So silicone elastomer before was processed mainly by extrusion or calendering, but also compression, and now mainly by injection process. But today, you can also print silicone thanks to the with additive manufacturing. And in order to do that, you have mainly three processes the UV vat technology, jetting, or also extrusion process. So in order to print the silicone, you have to manage mainly two things: the rheology or the viscosity of the product and the chemistry of the curing. For example, for the vat process, you have to handle a very low viscosity product, and you will cure it mainly by photopolymerization. If you take the material jetting, you can use higher viscosity, and you can choose different curing chemistry to get the parts, from photopolymerization to condensation, or also hydrosilylation, also called polyaddition. And in the case of the extrusion process, you have to use very high viscosity product in order to print it, and you will use also different kind of curing chemistry like photopolymerization, condensation, and hydrosilylation. And if you don't manage very well, in this case, rheology and the curing, you will get something like that. As you can see in the middle of this slide, if you don't manage very well the viscosity of the product and the chemistry of the curing, for sure you will don't get the part that you want, and it will collapse during the curing or the printing. So it means that you have to manage very well. So it's our business. You have to manage very well the viscosity or the rheology of the product and the chemistry of the curing in order to get what you want at the end regarding the shape of the part, but also the final performances. So if I focus on extrusion process, so you know probably for the extrusion process, you have to extrude the material. In the case of the silicone, you will extrude the past at room temperature thanks to different processes. You have some example on the left on this slide for a mono-component system or multi-component system. Today, Alchem Silicone provide a new brand called AMSIL, and the products are mainly focused on extrusion process. And these products are divided in two applications. One dedicated to industrial application, and the other one dedicated to the medical restricted applications. Now, if I speak about industrial application, you will see that we provide two technologies, one based on one part system, and the other one is based on two-part system. So for the first one, the one-part system, this one is you will print it at room temperature, and the curing will occur also at room temperature and will be done thanks to the humidity. We provide a range of hardness comprised between 15 and 50 short A today, with tensile strength goes up to 6 MPa, elongation at break up to 500%, and present good adhesion on various substrates. And this series is really suitable for rapid prototyping, but also to do some small series with functional parts. So it means that thanks to that, you can test new designs in real life, I would say, and start to use it for real applications. Regarding the other series based on two-part system, so you have to handle so two products mixed together during the printing, and you will cure the part after the printing in our oven at high temperature. We are developing a full range of hardness comprised between 20 and 70 short A, and we provide today product with 50 and 70 short. The mechanical properties goes up to 10. Regarding the tensile strength goes up to 10 MPa, elongation at break up to 900%, and present very good compression set, good fire resistance, and these products are mainly transparent, but you can also color it. So now I will show you some technical results regarding the printing part, and I will start it with some mechanical results. So here you can see some tests done on dog bone samples. So we choose to print dog bone with 100% of infill, but with different, I would say, different geometries, with grid, rectilinear, and linear geometry. And we will compare the results. So we tier on the sample, and we compare the results to molded parts. So you can see on the graph on the right here, in blue, the tensile strength at break, the modulus at 100% of elongation, and the elongation at break in orange. And as you can see here, the printing process have a strong impact on these results. But if you choose the right process to print your dog bone, you can recover the initial properties of the molded part. And that it's not due to the material himself, but it's due to mainly to the defect that you will introduce during the printing. That's why you need to manage very well the printing process. You can see on the picture in below of this slide, two dog bone, one with not so much defect, and the other one with lot of defects that will lead to poor mechanical properties. But the beauty of the 3D printing is to manage the infill of the part. If you take into account the molding process or injection, you will have a full dense part. With the mechanical properties due to the material that you will use. However, with the 3D printing, you can choose the infill that you will put inside your model. You can choose the amount of the infill and the geometry. So here you can see two traction sweeps, the same material, but one on a dog bone molded, and the other one printed with 30% of infill. So you can see here the mechanical properties that you get, and you can see that here that the mechanical properties are mainly due to the printing process and not due to the material. So it means that if you manage very well your printing process and the material that you use, you can imagine lighter parts with new mechanical properties. Another example to show you that. Here you have different pictures of the same material and different shape with different infill. And you can see here clearly that the rigidity and the mechanical performances of the part will depend on how you print inside the part. And now you can imagine if you combine a wide range of hardness of material, such we are providing today, with the full possibilities of the printing process, especially regarding the infill. So now it's opening, I would say, a very wide range of mechanical properties and new applications. Another example to show you the benefits of the silicone with 3D printing. Here you can see here not very high volume part, but more textile-like part. And it shows you what kind of elasticity you can get thanks to this technology. The softness, the feeling that you will get with such a parts. And thanks to the low energy of the silicone, it's really compatible with different substrates. So you can imagine infinite design and combine together different material and imagine new solution and innovate for different applications. When we speak about 3D printing, clearly now we have to take into account how to design the part. Because up to now, the design of the part was mainly based on the, I would say, old processes like injection, extrusion, or molding. But clearly, for additive manufacturing, for not only for extrusion, but for the different process and the full panel of material. Now we have to rethink and rebuild new rules to design the part in order to use the full potential of 3D printing. And now one of the main things that you have to take into account when you speak about extrusion process for 3D printing, it's the overhang. Here, you can see here the example of an ear with a very tricky zone regarding the overhang that you can see here on this slide in red. But if you combine the right rheology and the right curing of the product, you can print this kind of geometry even without support material. It's not impossible. And now, just to fix the idea and to show you how how is printing by extrusion the silicone, I will show you two examples of time-lapse. One about, the first one is about a simple ring. So I hope it will work or not. Mm-hmm. Yes, here we go. So you can see here the kind of aspects that you can get with such a material. And now I will show you a second time lapse, a second example about a model of an aortic valve. And clearly on this model, you will have some tricky zones regarding very thin wall and also difficult overhang, but it's not a problem, it's not an issue. We can print it very well. Thank you for the attention for this part. Michael?
Right, great, thank you for that, and nice to see the printing in action there. You've certainly got people's minds going, so there are a lot of questions. I'm going to try and get through a few of them here, but if we can't get through all of them, then we'll come back a bit later to the end of the event and we'll take the questions then. So let's go through a few now. So first off, is there an additive solution to achieve proper adhesion for silicon resins when curing on a high energy surface, such as polyimide films, so Captain, for example?
Can you repeat the question, please?
Sure. Yeah. Is there an additive,
just to be sure,
it's an additive solution to achieve proper adhesion for silicon resins when curing on a high energy surface, such as polyimide film?
Yeah. Yes. We can have good adhesion on different substrates. We can manage it.
Okay, good to know. If you want to know more details, make sure you catch down Damien at the networking session afterwards and give you much more info on that. Could you please answer how much degree of durometer can be printed? Is there a range of durometers to print out with 3D printing? I think you did tackle that a bit, didn't you, in the presentation? So,
yes. Today we have a very wide range of hardness, but you have to take into account also that the softness and the rigidity of the part at the end will depend on the hardness of the material himself, but also on how you print the parts. So you have to think about how to combine together the hardness of the material, but also how you print the part to get the right performances that you need.
Okay. Are your 3D printable silicon materials biocompatible for medical or pharmaceutical use? And do you have test data available?
We are developing some product for this kind of application. Yes.
Okay. So coming soon. What are the testing standards used to obtain the mechanical properties of these AM silicons?
We use mainly dog bone H2. I would say it's industrial. We base our test on industrial test. So if needed, we can provide some results later.
Mm-hmm.
No problem.
Okay, Christopher, hope that answers your question. We also have a question here. Could you please discuss about the applications of 3D printed micro or nanostructures in silicon?
Nanostructures.
Mm.
Oh, it's another word. Yes, there is some things about that. Maybe we can discuss it later because it's really specific for this kind of yes, for this kind of application. Yes.
Okay. Well, look, I'm going to leave the questions there for now. We'll come back to these at the end. And I'd like to invite Carsten back, please, to take the next section for us.
Yes, thank you very much, Damien. Thank you very much, Michael. So now we were going, after this technical session, we were going forward to see to what extent this is applicable in real cases, in use cases. So if you have a look at those two photos to the right, you see a truck and you see a distribution line, a conveyor belt, and what is the common denominator of those two ones? It seems to be a failure, because a truck is a vehicle off-road when the hood is open, and when on a conveyor belt nothing is passing, it means that you have a disruption somewhere in the line, and that can be due to tiny little parts, as we have seen in the application, like a seal or a joint or technical part that might be of elastomeric nature. So this is causing big problems for a minor technical part, you might say. So in that respect, silicons, as with these, we can print them now directly with 100% of the right material. So having this advantage of really print on demand and adding on there the digital inventory, where you wouldn't sit it there, because you will print it when you need it, where you need it, in order to make that happen. So this is a clear example where now this technology can handle materials made out of silicons. Might it be here in the spare part management, but in general also maybe in MROs activities all over the place. Damien, next. Innovation is another sector which is something we all know the pressure is on to reduce the time to market, to make things happen in order to have the new profitable business coming online very soon, the quickest enough. So there's this activity about prototyping, reduce it down. When we have it in our traditional business, where we supply silicons for injection molding or casting molding, compression molding things, we know that times can take quite a long for making those prototypes. And we have that maybe 4 to 8 weeks in certain cases. Whereas if we drill it down, then using the direct printing of the right material, we can have it much shorter. Here in the example, we have picking up 14 days in that. And that's the possibility now, that you're going to use the real material immediately for prototyping. So not wasting prototyping material for molds and for the parts, but you use immediately the right material, not just for form and anesthetics, but immediately for the right function that can be tested, and even for the costing to make things, if they are manufacturable or not. Adding on iteration are much shorter to make, to optimize the part, even going for small runs, pre-launches, things like that, immediately with the right material. Damien? So we've been talking about soft robotics for a long time, things out there in various dimensions, soft robotics.
Sorry.
And their silicons are known as a material. What you can see here is a simple part of an actuator for a gripper, but you can imagine that through the right design to become much more sophisticated, or having the possibilities to introduce in their sensors that will allow human-machine communication much better, or more sensitive grippers than the standard, I would say, pick-and-place robos that we have there. That in the future will play a major role, and their silicons with their unique properties are material of a high solution in there. Next one. So when we're talking here, what we're presenting you about the extrusion technology, it's something that allows the use of other materials. So you combine it. It's not just combining different grades of silicons to join them to make an elastomeric part, but also the possibility with this technology to use other support materials. You could imagine, like you see it here on those photos, having different shapes, different structures, but in those shapes, the silicon could be formulated to have conductive properties, which might be an attractive case for wearables in this industry, or you have embedded electronics in there where you would use the properties of silicons as an insulating material in that respect. So that's one of the things where the extrusion technology combined with additive manufacturing, design possibilities and silicon formulation might be of interest and has shown a clear interest in applications. Next, please. After those examples coming out of the more industrial applications, we have taken as a last one something out of the healthcare. As said at the beginning, we know that personalized healthcare is something that is coming along. The technologies are really driving to go there. And that is the point where if we take on silicons as a high performance material, then we are touching ground where silicons are used already in many, many healthcare applications because they have these properties of being biocompatible, odorless, and others, but also that they have the possibility to mimic the texture and the feel and the elastomeric behavior of parts of the human body, like organs and others. And two examples, for instance, we have anatomic modeling as something for training of surgeons, allowing them to have a real physical feel for when they do the training, and that would allow them to not train themselves on animals or on dead bodies, something that people really want to have been disappearing out of the landscape. So we need the right models having the right properties. And the other thing is the pre-surgery planning, as we said, patient-specific, in order to allow afterwards a higher success rate for the surgeon, for instance, when he is able to envision his intervention before going into the operating theater, and then being prepared to have that, which allows the higher success rate for the surgeon, a better recovery rate for the patient, which is the prime thing afterwards. But at the same time, being clear, this allows to save money on the stay in the hospitals and save the bill on our social security systems as well. So these were some of these business cases that we wanted to show to you in general. So next, please. Over the course of this presentation, we have been showing you how Alchem has been taking up the challenge of using additive manufacturing, these possibilities, and combining those ones with the unique characteristics of silicons in, by the way of, as we have taken as example, the extrusion technology. And this is what we wanted to go forward with, that in showing that we have in our respect an open market approach. So we are providing raw materials and expertise that we have been developing to our customers. We are not a printer. We have the expertise because we have application labs around the globe, but we will go forward and would like to go forward with a collaborative approach, defining the business cases like what we have been showing you in some examples here, getting down to the technical requirements in that respect, and afterwards allowing our customers to implement that solution at their premises, at their facilities, in order to allow them to leverage on all those good things that additive manufacturing combined with silicons can do in that respect. So this is what we are striving for. Next, please. And to conclude, it is really that we want to provide our customers with the expertise to build their own competencies into that, because that is, as Damien said, that is going to add the value to their businesses, to their service offerings, in order to make them leveraging really all these things, silicons and additive manufacturing combined. So this is the end of our presentation. And I think now I hand over to Michael and to Damien, and I think we are now touching Q&A, isn't it?
Indeed it is, and we've got a lot of questions coming in, so let's get straight into it. Most popular question so far is this: what printer are you using to print silicon? Is it extrusion based? Please share the details of the machine. So I think that's probably referring to the videos you showed there. I'd say we are working with different printer partners over the development. What we have been doing, there are machines out there, and they have each machine. Those machines have specificities, and what we do in general, we take the project of the customer and to see what machine would be the most acquainted to respond to the requirements of the customer. So depending really if it is needed for high technicity or lower average. But we can go into details into that if we do the networking or one-to-one in order to go further, dig further into those details. Excellent. Jessica's asking, are Alchem selling the material or the printer? If just the material, which printer do you use? I think we've answered a bit about the printer, but am I right in saying you just sell the material? You're not developing hardware?
Exactly, that's what I said through the last slide. We are advanced material provider with all the expertise. That's the reason why we have printers at our application labs. That's the reason why Daniel has made all his work around this application, those printers, in addition to the chemistry. So that's what we sell today, yes.
Okay, here's one for Damien, I think, which is, what are the advantages and disadvantages of addition cure silicon over photocurable silicons in 3D printing?
I would say a lot. I have some ideas in mind, like durability of the performances. You can imagine also for restricted application, today it's easier to get a certification based on polyaddition chemistry than photopolymerization sometimes. And after that, I would say the full formulation of the product. Today, thanks to the polyaddition, we can provide a very wide range of mechanical performances.
Okay. I'm going to combine a couple of questions because they're all alluding to the similar sort of ideas here. So is there a silicon for DLP vat printers? And is that something that Alchem offers? I.e., do you have the formulations for vat photopolymerization or inkjet?
Today we have been presenting our approach on the extrusion chemistry, and but this is not said that we don't have other technologies we are working on, as you have seen on one of the slides of Daniel when he said what might be appropriate for silicons to be used. So we are working also on the other technologies in that respect, and so we can discuss this further in detail maybe in the networking or in a one-to-one session.
Okay, so there we go. So we've been talking about extrusion here. So what's the minimum wall thickness that you can print?
The thinner thickness that we print, it's I would say 200 today by extrusion, maybe less, but if you have a small thickness, you will get more time to print the part. So you have to think about the productivity and the details that you want to print. But the lower thickness that you use commonly today, it's 200.
Okay. Are the silicon materials used in additives softer than PU-based elastomers or other polymers?
100% silicone.
Okay. Are 3D printed medical implants part of the scope of applications?
Due to the nature of silicons, I would say this is the ultimate goal that we want to achieve down the line. I would say I don't want to kill my silicon business now, but maybe in 20, 30 years, it will be replaced by bioprinting overall, as we know from some films we have seen about the vision in the future, as we all know. But yes, we are striving forward to go in that direction. But this is how to say, LTI applications are already very challenging in standard terms, but 3D printing will give an additional possibility and capability of using LTI applications with silicons.
Okay, question here about what data do you have on compression set as a function of deflection, time, and temperature, and which grade has the best capability for static sealing?
We have some data regarding compression set, and for sure, silicone chemistry are really suitable for for application that requires a good compression set, because it's not meltable product, as I mentioned, but it's pure. So you can imagine that you will get very good compression set results. But also it's strongly depending on the test himself, temperature and the time. So maybe we can discuss later more deeper about what are the needs and which product could be suitable for the application.
Mm-hmm. And a final question for now, which is, can you please comment on the filament to filament and layer to layer bonding strength, which is usually an issue in thermoplastic extrusion 3D printing? Yeah. Sure.
But the beauty of this technology is that you print a liquid part. So thanks to that, you will have a very good interaction between the line and the layer. And as you cure the material after that, you will have a chemical binding between each layer and each line. So you will get a very good performances at the end, for sure. And it's not an issue like thermoplastic. The main issue with thermoplastic, it's interlayer binding, as you mentioned. But for sure, with silicone, it's not an issue, because you have a strong chemical binding between each layer.
Mm-hmm. Okay, well, thanks to the audience for some very informed questions there, and please don't go anywhere. Do stay for the networking. I'd just like to thank Damien and Karsten for joining us today.
You're welcome.
Thank you very much.
And
thanks for the audience.
Please look for the tables marked Alchem, where Karsten, Damien, and other representatives from the company will be happy to answer your detailed questions. So please stay with us as we go back to the networking now, and bye from me.